All right, welcome everyone. Last week of classes, last section too, even though we do have 2 days for it, right? So 16.9 is all about the divergence theorem. And we'll have today and Wednesday's class to really master that. And then Friday's class will be some final exam review. I mentioned last Friday that I've started to publish some of the resources for studying for the final exam. So I invite you to I published a lot of these true-false questions that you can take a look at, along with the solutions. I've also published the review document for next Friday, or sorry, this upcoming Friday's class on D2L, and then finally this the checklist. So please do take a look at these things. Administratively, same old to some extent, right? We have our last quiz coming up this Thursday. That'll cover this 6.8 and 6.9, so Stokes theorem and divergence theorem. But before we get into the particulars of divergence theorem, I thought it'd be good to maybe step back and look at chapter 16 as a whole. So to that end, I've included this kind of concept map. Is quite often what these are called in education circles. And show you that there's kind of a strong analogy between line integrals and the storyline there, along with surface integrals and the storyline there, right? So we first learned the basics of line integrals back in 13.3 when we brought up arc length. Of course, we expanded on that, right, and said, well, you can add up other quantities along a curve rather than just the length of the curve, right? You can add up plankton along the curve. You can add up mass along the curve, right? And so in 16.2, at least the first part, right, we were talking about line integrals with scalar functions. We expanded on that and said, well, chapter 16 is all about these vector field things. You can also do line integrals on vector fields. And so the main use case for that was work, right? And so we talked about the work done by a vector field along some curve, and that was the main second half of 16.2. So line integrals with vector fields. And then finally, we ended with, hey, there are some tricks that you can do in some cases, not all cases, but in some cases, there are tricks that you can do in order to make the evaluation of line integrals a little bit faster. And so you had the fundamental theorem of line integrals with 16.3. This was in the case that you had a conservative vector field. And then in 16.4, we had Green's theorem, right? And there were a couple different flavors on this as well. But these were cases, right? For Green's theorem, you need a closed curve. For fundamental theorem of line integrals, you need a conservative vector field, right? So again, they don't always work, but when they do, they quite often make your life a little bit easier. Now, the second half of chapter 16, we're talking about surface integrals. So we first start to talk about surface integrals really with surface area. And surface area is kind of analogous to arc length, right? It's kind of this natural measure on whatever structure you have. So rather than a curve, you have a surface. We then upgraded that and said you can add up other quantities on that surface rather than just how much area there is. For instance, I did that silly example with snakes on a plane, right? And so if you have some snake density function, you can add up the snakes on the plane. We then said, well, chapter 16 has something to do with vector fields, and that there's an upgrade for surface integrals in terms of vector fields, and that was flux. So 16.7b was all about flux. And now we are kind of well into the tricks, right? So these final two sections in chapter 16 are really specific cases of how can you evaluate out surface integrals. The first is Stokes theorem, which we spent a lot of time with the last two classes, and now we're moving into divergence theorem. So divergence theorem is kind of very similar to Green's theorem, back here from line integrals days. For Green's theorem and line integrals, you need to have a closed curve. And you probably saw in the pre-class video for the divergence theorem, you need to have a closed surface. So divergence theorem only works if you have a closed surface, but when it works very nicely, and it'll make our life a bit easier. The final thing that I had on this page was a little bit of a conceptual true-false style question. And this is the combination of Stokes theorem, right? So this quantity on the left-hand side here is what we saw again and again in Stokes theorem. Remember this del cross F, that's the same thing as curl. And then we're asked, well, what if you try to apply Stokes theorem to not just any old vector field, But what if you tried to apply it to a conservative vector field? How do these things intermingle with one another? And the question is, right, well, the hypothesis is, well, maybe this is zero. So my claim is that this is a true statement, that this is in fact equal to zero. Can someone tell me maybe the fastest way that you can quickly see that this must be zero? Anyone able to get it? Yeah? Yeah, so for conservative vector fields, remember the main way that you tested this was that you took the curl, and if it was a conservative vector field, when you calculated this out, it was equal to zero. And that allowed you to then use the fundamental theorem of line integrals. And so therefore, if this quantity here is zero, and it's the zero vector, right? Well, then when you add up zero a bunch of times, right, you're of course going to get out zero. So that's one way, that probably the fastest way that you can see that this is true. The other thing is that for boundaries for these surfaces that we always apply Stokes' theorem to, so let's suppose that you have some interesting surface here and some interesting boundary, right? This would be, according to Stokes' theorem, equal to f dot dr, oops, where this curve that you're integrating over is the boundary curve of the surface. Now, the nice thing about boundary curves of surface is that they need to be closed. And so then if you know that this is a conservative vector field and you apply that this is supposed to be f of b minus f of a, the ending point minus the starting point, well, whatever the function's value is, right, at b, it's the same as at a because it's a closed curve, right? It starts and ends at the same spot. And so who cares? Maybe it's 5 in both of these cases, right? In which case it's going to be 5 minus 5, in which case you get out 0. So that's kind of the slower way that you could also get the same result that if you tried to apply this fundamental theorem of line integrals. So you can see that when we do Stokes' theorem problems, we haven't really done them with conservative vector fields so much because the result's very boring, right? It's just always 0. So this is how these two theorems kind of intermingle with one another. Yes. All right. Any questions administratively or kind of conceptually or anything before we jump into the divergence theorem for today? Okay. So then, the divergence theorem, the final big theorem here, we had this alternative form of Green's theorem. And like I said, really Stokes' theorem and Stokes' theorem and divergence theorem are both upgrades of the two different flavors of Green's theorem. So in this second half of 16.4, when we were talking about flux, right, we had this line integral here, and we found that this was equal to p sub x plus q sub y, the double integral there. And of course, these are the, if you just have p's and q's, that's actually the same thing as the divergence of f. Right? So we're just applying this del operator dot f. And so you take the partial derivative with respect to x of your first component, partial derivative with respect to y of your second component. And since there is no third component, it'd be like the partial derivative of z of 0. And so that's just 0 there. And so with this idea, we can upgrade and figure out now for surface integrals, when we're calculating out the flux, the story is going to be very, very similar, right? That we can then upgrade this. And so for the surface integral for flux, that this is equal to then the triple integral of our divergence. So this is how we can take this 2D theorem, Green's theorem, and upgrade it to a 3-dimensional theorem. How can we do this in more dimensions? Well, that's going to be the divergence theorem. So again, divergence theorem is just a 3D upgrade of the flux version of Green's theorem. Again, the main condition, just like for Green's theorem, for the divergence theorem here is that you need to have a closed surface. So it completely surrounds some 3D region because you need to make this exchange between a double integral and a triple integral. So the S here is the surface. The E is supposed to be this 3D region that the surface completely surrounds. So if your surface does not completely surround some 3D region, doesn't completely enclose it, then you cannot apply the divergence theorem. And you need to use one of the other ways, right? Maybe from 16.7, for instance, evaluating out surface integrals. So again, the divergence theorem is a trick. It's nice when it works. It helps us evaluate out these surface integrals faster. It doesn't always work, right? We had to learn 16.7, and we're not making 16.7 obsolete. There's still good reason why you would need to be able to perform those sorts of calculations. All right, and then I had an example from an old final exam here of an example, right, how to use the divergence theorem. So we had some plane, right? So E is a solid in the first octant that lies beneath the plane. S is the boundary of E. So it completely surrounds E. So S consists of the four triangles, right? Not only the slanty one, but also the kind of these backsides as well. So we had a vector field, and then we used the divergence theorem. So we, right, instead of our surface integral, instead of evaluating it out that way, which, by the way, there's 4 different surfaces here, so this would take forever if we didn't employ some trick. We were able to then trade that in for a triple integral, which a little bit easier, especially because there's only one of them instead of 4 of them. And the integral that we need to evaluate out was of the divergence of f. So we calculate out the divergence, and then we could go ahead and set up our integral. So like I said, set up, but do not evaluate. Any questions on this problem here? Well, again, this is kind of the big theorem of the day. The rest of today's class is really just getting more practice with this, seeing more ways that this can be represented in problems that you could see on homework, quizzes, exams, things like this. So let me go ahead and transition here into our problems for today. And you can see my only objective for today is just apply the divergence theorem to more problems. So why don't we go ahead and start off with this one here. We want to evaluate out this surface integral. We're given a vector field. S is the surface of the region E bounded by this parabolic cylinder and 3 planes. So this again is some completely surrounded region. If you wanted to evaluate out the surface integral as it stands, you would need to take each one of these pieces, so maybe the backside here, calculate out its normal vector, right? Because again, this ds here has a normal vector. You'd have to determine if you're going to be doing this explicitly with a z equals equation, or if you had to parameterize this. You'd then need to do the same thing for your bottom side with its normal vector. You need to do it for this slanty side here with its normal vector. And then you need to do it for the curved side, this kind of parabolic cylinder bit with its normal vector. Again, each one of these you would need to figure out, do I have a z equals style equation? Can I use the explicit form for evaluating out surface integrals? Or do I need to parameterize my surface and find the normal vector by taking a cross product of tangent vectors? So you can see, even though that this problem does not say use the divergence theorem, it would be kind of completely unreasonable to do anything else, that it would take forever in order to solve this in the typical 16.7 style. Luckily though, this does completely surround some 3D region. And so therefore we're allowed to trade in our surface integral in for a triple integral of the divergence of f. So let's go ahead and calculate out our divergence here. For our first component, p, we're going to take an x derivative. For our second component, q, we're going to take a y derivative. And for our third component, r, we're going to take a z derivative. When we do that, this simplifies down very nicely into just 3y. Still though, now we have to evaluate out a triple integral. Right? An inevitable question that I get asked, about the final exam is, how much of the final exam is new content versus, right, the stuff after exam 3, versus how much of the final exam is previous content, right? Because it is cumulative, it covers everything, right? But you can notice that if I ask you a divergence theorem problem, right? Well, first of all, I guess technically you've had to do some dot product of this del cross, this del dot f sort of deal. You've had to do some partial derivatives, right? So that's like 14.1 or 14.3. But now we have to do a triple integral here, right? So I really don't need to ask you a separate triple integral question. I can ask you a divergence theorem question. And this is kind of now naturally embedded in technically stuff that we've done before, right? But it's of the flavor of a divergence theorem question. So it's hard to answer this question when I get it, how much of the final exam is new stuff versus how much of it is old stuff, because the new stuff that we're covering covers so much of the old stuff. And so consequently, if I had to ascribe, some number to it, I would usually say maybe around 70% of it or so is new stuff. But there's that's some mean and there's some standard deviation associated with that. I've seen final exams completely reasonable that, only have 50% of it is new stuff, quote unquote. And I've seen final exams where, 80% or plus, could be even this new stuff, because again, the new stuff covers so much of the old stuff. I don't need to ask you a triple integral question when the divergence theorem makes you do triple integrals. Okay, well, let's evaluate this one out, just like we did back in chapter 15, right? So, okay, I need to evaluate out this triple integral. I need to decide, am I going to integrate with respect to z first, or y first, or x first? Or should I switch this into cylindrical or spherical, right? There were kind of these 5 different ways that we could evaluate out triple integrals. So seeing this, it doesn't really scream to me cylindrical or spherical. So I want to eliminate those first. If I don't see any other better reason to do things, I've already told you guys that typically I like to do dz, dy, dx as my starting order of operations for triple integrals. However, in this case, I believe that there is a compelling reason not to choose this order. Can someone maybe tell me, when you look at this, what is my compelling reason? Why should I not do the z first in particular? Yeah, well, I saw your hand first. Oh, okay. So that's clever. I like that. The answer that I heard here was that you have a y in terms of z, right? So the picture was kind of nice to us, and it solved this one y equals, right? Maybe you can imagine if it wasn't so nice to us, right, and it just gave us y plus z is equal to 2, right? So it could give us this as well. But I like your reasoning as well. So having a y equals should be a bit suggestive. It's maybe pushing you towards maybe a y equals integral would be better first. Does anyone have another? Yeah, what were you going to say? Yeah, so when you're traveling in this z direction, there's only one way that you enter in. You're going to be entering in through z equals 0. But when you exit, depending on where you are in the square, sometimes you may exit through this parabolic cylinder bit, which has the equation z equals 1 minus x squared. Or sometimes you may exit through this plane bit here, which has the equation z equals 2 minus y, I suppose. So your exits may be different depending on where you are, and therefore you would need to split this up, and it'd become quite painful to solve this, in terms of z's first. So that's kind of graphically why. And again, algebraically, I like, first of all, algebraically, you see a y equals. That's a good indicator. But you also see 3 equations here that have z's in them, right? So that means that there's not going to be just one entrance or just one exit. I don't know, right, without the picture, which one's going to be having the multiple entrances or multiple exits. In this case, it happened to be the multiple exits. But the fact that there were 3 z's in these equations was kind of alarming, right? So that's kind of the algebraic thing that should make you a little bit worried. All right, so if instead I was to integrate with respect to y first, do you guys have any questions here? Okay, I just wanted to make sure I didn't miss something silly, Sometimes when I hear a lot of camaraderie or whatnot, it's because I made a silly mistake. All right, so if we integrate with respect to y first, right? So I'm traveling in this y direction now. We can see that we're going to enter in through this back half. and we're going to exit through this front half, right? So there's only one entrance and one exit. The other thing is when we look at all of our equations that were given, right, I only have two equations that have y's in them. So again, that's rather suggestive that, again, we're only going to have one entrance and one exit. So that's quite nice. So let's go ahead and reorder this a little bit. I want to do dy first, and then I'm not sure yet, but maybe dz is going to be fine next, and then dx. I'm just going to write something down, and again, I can just erase it and change it if I don't like it. So I'm going to enter in through y equals 0, and I'm going to exit through y equals 2 minus z. So that's my entrance and my exit there. Now I need to smush this down so that there are no more y's left, and all that's left are x's and z's. So if I was to take this and smush it down so that I can view it in the xz plane. So when I take this and I smush it down, I think all of it's going to lie here. It's kind of actually a part of this back half, right? So if I was to smush this into the xz plane so that there are no more y's, I think it looks kind of like this hump here in the positive z direction. And all of my shadow or all of my residue or whatever, right, lives inside of this hump here. And looking at the equations, some equations jump out to me, right? Of course, the z equals 1 minus x squared is probably this hump. But then also there's this z equals 0. And between those two, right, the z equals 0 and the z equals 1 minus x squared, that's going to help me determine, right, my bounds for x, right? How far can I travel left and right and stay in this region? Well, it turns out if you solve that, right, you get between -1 and 1. So if I was to finish setting this up, right, my z's are going to range from 0 to 1 minus x squared, and my x's are going to range between -1 and 1. So again, traveling in the z direction, how do I enter and how do I exit? I enter in through z equals 0, and I exit through z equals 1 minus x squared. And then my x's range from -1 to 1. All right, so here is my setup. We'll do a couple lines of the evaluation here, but again, kind of the most important thing is the setup for this, I think. That's the most difficult part. So this is kind of just the tedious part more than anything, so I don't want to spend too much class time on this. If I integrate with respect to y first, I'm going to get 3/2 y squared. And let's go ahead and maybe combine steps and input in my bounds. So 2 minus z, and then of course 0 squared here, which would just be 0. Don't even really need to write that one. Now you can see that if I want to do the next line to integrate this, right, really I need to maybe evaluate out or expand out this 2 minus z quantity squared. So I'd like to go ahead and break this down a little bit, FOIL it all out. And so what I'm going to have, 4 minus 4z plus z squared, once I have all that FOILed out. So again, you can see this isn't maybe the conceptually difficult part or anything like that. It's just more tedious than anything. Let's go ahead and bring out this 3/2. We can integrate this z. So we're going to have 4z minus 2z squared plus 1/3 z cubed. And I tried to leave myself enough room here that my next step is that I want to evaluate that from 0 to 1 minus x squared. So if I was to just swap out everywhere I see a z, a 1 minus x squared, I would get something like that. This is probably the point where I'll end. I'll say that when I evaluated this in my office, I got 184 divided by 35. So if you want to do this, if you find value in continuing out this integration to get a final answer, at least when I did it, I got 184 divided by 35. So if you get that as well, you have the right answer. But again, the main things that I want you to take away from this problem more than anything is, first of all, when do I know to apply the divergence theorem? This problem did not say use the divergence theorem. We are in a class, of course, that's all about the divergence theorem, and so your mind's going to naturally go there. But if you saw this on the final exam, and you have multiple options of how to evaluate this out, how do you know to use the divergence theorem? And then the second thing, right, is that this triple integral was, it took a little bit of time to set up. And the setup of this was interesting. But if I wanted to make this a reasonable quiz or an exam question, right, kind of less similar to the one that we saw in the fall semester 2001 that I did in the pre-class video, I'd probably say set up, but do not evaluate. And then this becomes a perfectly fine final exam question, right? I get all the interesting stuff without any of the tedious long evaluation that this one requires. Good. Any questions on this one here? All right. Well, let's go ahead and try another one then. This one's considerably faster. I could turn this one into like a multiple choice style question. And so why don't I give you guys actually 2 minutes or so. Please try this one on your own. This was back in a semester, I had to write the exam all on my own for a small section. On a previous exam, they calculated out the volume. So that's why that hint's there. But so yeah, please take 2 minutes to try this one on your own. See how far you get. This is another problem where the hardest thing about this problem, I would say, is deciding what to do. And again, kind of we're cheating ourselves a bit by being in a class that's all about the divergence theorem, right? So of course our mind naturally goes to the divergence theorem in today's class. But right, imagine this shows up on the final exam or something like it, right? Nowhere in here does it say divergence theorem. In fact, nowhere in here is there even a double integral whatsoever, right? So the first thing is, right, we need to read this and say, it says calculate the flux, right? So we need to remember that the flux here for some surface was given by this surface integral. We calculated out the surface integral, you know, in the traditional sense from 16.7. However, right, we're now learning that here in 16.9, if you have a completely enclosed region, right, your surface completely encloses some 3D region, then you're allowed to trade this in for a triple integral according to the divergence theorem. And it would be the divergence of your vector field is what the thing you should be integrating is, right? So what should you put here? Well, it should be the divergence of F. And so we need to look at our vector field, taking the partial derivative with respect to x of our first component, the partial derivative with respect to y of our second component, and the partial derivative with respect to z of our third component, which all turns out to be very nice. 3 plus 1 minus 2 is just 2, which you can bring out if you'd like. And then there's a hint that says that the volume enclosed by this region is some quantity. Well, the triple integral of 1 is just volume. And so this right here would be the final answer. So like I said, this would be a perfectly fine like multiple choice style question. I'm not sure if it warrants the full strength of a standard response style question where you show a lot of work. There's just not a lot of work to be shown, right? It's kind of making the decision to, first of all, set up your flux integral, realize, hey, I can apply divergence theorem to this. And then, oh yeah, the triple integral of 1 is just volume, right? If you realize these things, there's not a lot of work to be shown here. This one's a little bit contrived, right? Because I had to tell you what the volume was in this case. But we also know many structures, the volume equations of these things already, right? So if I gave you a sphere, right, instead of this weird like prism thing, right? If I gave you a sphere, you could pull off the same trick, right? Because the volume of the sphere, 4/3 pi r cubed, that's on our formula sheet. Or if I gave you a pyramid, right? You know a volume equation for a pyramid, or things like this. And so there's plenty of questions that could be made into like a multiple choice style question using volumes of well-known solids. Really quick, an alternative question here. Suppose I did everything the same, but I said calculate the flux of our vector field, and I said inward through S, blah, 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 right? So all I do is I change, instead of calculating out an outward flux, I'm interested in calculating out an inward flux. How does that change my answer? Yeah, so I think I heard it whispered. You need an extra negative, right? So divergence calculates out how much is going outward. Remember divergence, right? When we calculate out this div thing, that if something's expanding, if you have a positive divergence, more is heading away from it, right? It's an outward flux. And so to account for that, right, you just need to make it negative. So if you were interested in an inward flux, f dot ds, right, where this ds is now an inward pointing normal vector rather than an outward pointing normal vector, this would just be equal to the negative of, and you could still use your divergence theorem, essentially, but now you're just off by a negative because you're calculating out inward flux rather than outward flux. And so, right, our final answer would just be the negative of this. So even though the divergence theorem, and likewise Green's theorem back in 16.4b, was used to calculate out outward flux, and it's like worded and everything in terms of outward flux, it's not useless when it comes to inward flux, right? You can still calculate out inward flux, you just have to multiply by a negative. Perfect. Good. Any questions on this one here? So far, is divergence theorem easier or harder than Stokes' theorem? A whisper for easier. You're brave saying that. Thank you. But yeah, so that's what I think I said last week, is that hopefully the divergence theorem will be a little bit nicer than Stokes' theorem, right? You don't have to think a lot about normal vectors and parametrizing boundary curves and all this sort of stuff. So in general, I typically find students say it's a little bit nicer. All right, yeah, let's try another one here. We have a vector field over the surface S, where S is the cylinder, x squared plus y squared equals 1, capped by the planes z equals plus and minus 1. And then it asks, is the net flux of F from the surface positive or negative? What is the value of flux across S? And so I guess I wanted to bring this up as some important terminology. The difference between capped versus cut. So when it says capped by these planes, that these planes are included in our surface. So in our case, again, we have a cylinder, it's capped by these planes. So these planes are included in our surface. They are part of S. In comparison, we've seen other times where we take the cylinder, and again, we don't want it to go on forever. Otherwise, your answer is probably just going to be infinity, right? If you add up lots of stuff forever, it's going to be infinity or negative infinity or something like this. But so in order to not let it go on forever, we've also brought up the word cut, right? In which case, it's not really that these are included in the surface. It's just that's where the surface stops. And I need to tell you about where the surface stops in order for it not to go on forever. And so the difference between capped versus cut is very important. Because capped, right, when these are included, it's not just the cylinder itself, but you also include on the top and the bottom here. Now this is a closed surface. It completely surrounds some 3D region. And the divergence theorem can be applied to this surface. On the other hand, if it says cut, right, then we can't apply the divergence theorem because it's not completely enclosed some 3D region because we don't have the top and the bottom. And so in that case, you'd have to use 16.7 methods in order to evaluate out that problem. All right, so some key terminology there. It asks, is the net flux F from the surface positive or negative? And so, well, our net flux we can calculate out just from this divergence thing. So if I calculate out the divergence of my vector field, well, again, for my first component, I need to take an x partial derivative. From my second component, I need to take a y partial derivative. Again, all these things are going to be added together. We're doing a dot product here after all. And then from my third component, I need to take a z partial derivative. So my flux, right, and divergence is just flux at a point, right? Notice that my divergence here is always going to be positive, or at worst case 0, right? Because it's the sum of two squares. It's x squared plus y squared. So x squared is going to be a positive, or again, worst case 0. And y squared is going to be a positive, or worst case 0. And so when you take two positives and you add them together, we know that the result is going to be positive. So overall, the answer here is just going to be positive, right? This would make a fine true-false style question, right? You could just say the net flux is positive, true or false, right? In this case, it's true. All right. Of course, we could ask for what is the value, right? What is the value of the flux across S? Again, in this problem, it doesn't even have an integral. Oops. Right? We need to remember that the flux here is the same thing as our surface integral. Because it says capped, and that we have this 3D region completely surrounded by our surface, we know that we can go ahead and exchange this in for the divergence of F. Now I know what the volume of my region is, right? But unfortunately, this is not going to be the triple integral of 1. So that doesn't particularly help me. So that volume trick only helps when you have the triple integral of 1 or the triple integral of a constant, right? Because if you have really any old constant, you can basically just factor that out, right? This is a property of triple integrals that you can move them to the outside there. So that's not really going to help me. However, in this case, right, it's not so bad for this triple integral here, right? X squared plus y squared. And our surface or our region that we're surrounding is inside of this cylinder. And so we have to think about, again, when we go to evaluate out triple integrals, just like we did in chapter 15, I could integrate with respect to z first or y first or x first. I could also use cylindrical or spherical. And I hope that because we're in a part of a cylinder, right, that everyone's leaning hard towards cylindrical here. Also, we see the x squared plus y squared here, right? So all of this is kind of pushing you to, how should I evaluate out this triple integral? Well, I should use cylindrical coordinates. Lots of things to talk about here. But the first thing that I want you to do is yell at me. Why do you yell at me? Jacobian, yes. So even when we're here in chapter 16, right, on the final exam and whatnot, again, it's a common mistake that I see is that people somehow forget, and it's on the formula sheet too. You just have to look at the formula sheet, right? But they somehow forget, right? They go kind of blind for a second here in chapter 16. They forget that we're just doing a triple integral like we did back in chapter 15, that nothing's really new here. And so whenever you convert into cylindrical or to spherical or whatever, right, you have to include in this extra integration factor, this Jacobian thing, right? And so don't forget the Jacobian, this extra r, when you convert into cylindrical or spherical or what have you. All right, the other stuff, the other bounds I hope are relatively straightforward. My bounds here, right, it says it's capped by this plane z equals plus and minus 1. So those are where my z bounds are coming from. And then we have inside of this cylinder. So if you were to smush this down into the xy plane and look at it head on, sort of deal, that this is inside of a circle of radius 1. So if I want to talk about inside of a circle of radius 1, that means my radiuses should be going from 0 all the way up to the boundary 1. And I need to go all the way around the circle. So my thetas are going to range from 0 to 2 pi. Now, when I go to evaluate this, I'm certainly going to split this up. My function, my integrand, what I'm integrating, right, is just r cubed, which of course that can be written as 1 times r cubed times 1. And so now I've split this up into a function of just thetas, a function of just r's, and a function of just z's, all multiplied together. And my bounds are all constant, right? And so whenever that happens, you can perform this trick. If they're not constant, of course you can't. So there's plenty of times where we can't do this trick, but it's nice, you know, when it happens, because then the evaluation is quite fast. And so if I evaluate out my theta integral, well, the integral of 1 would just be theta. Evaluate that from 0 to 2 pi, I get 2 pi. Likewise, the integral of 1 dz, right, is going to be z, and I need to evaluate that from -1 to 1. So basically, there's just going to be 1 minus a -1. So that's going to be 2. And then finally, when I integrate r cubed, I'm going to have 1/4 r to the 4th, and I need to evaluate that from 0 to 1. And so my answer at the end of the day, I'm hoping for a positive, and I indeed got a positive. Because after all, we knew what we were integrating was a bunch of positives. And so when we do a triple integral, when we add up a bunch of positives, the overall result ought to be positive. So this one I would probably classify as one where, you know, like I said, the first one here, if I was to make this a exam problem or something like this, I'd say probably set up but do not evaluate, because the evaluation is quite tedious, right? It takes a lot of time and there's not a lot of knowledge shown during this complete evaluation part. This one I'd say would be make more of a multiple choice style question would be fine. This one I'd probably say, you know, the evaluation wasn't so tedious that, you know, you could expect to do something like this on a quiz and an exam and it wouldn't take a ton of time. So I'd probably have you set up and evaluate this if I was writing this one up. Any questions? All right. Well then, I have one last challenging problem that I'll hopefully try to explain here. This one says use the divergence theorem. Use the divergence theorem. So of course, right, if it didn't say use the divergence theorem, then I've evaluated out surface integrals like this before, back in 16.7. This is a surface integral with a scalar function, right? Notice that this is not a vector field. It doesn't have components. You don't see like a bunch of commas and angled brackets or i's and j's and k's, right? This would be like adding up, like plankton or something. Sorry, well, I guess we're on a surface. So this would be more like the snakes on the plane sort of deal. Like we're adding up some snake density function on some surface, right? So the problem is, so divergence theorem gives us this sort of exchange rate between a double integral, here a surface integral in particular, and a triple integral. So this is what we're tasked with using. Oops. The only problem is that my surface integral doesn't have a vector field. I don't know what to take the div of. And that's why this is, I've labeled this as a challenging problem, right? Because I need to spend a little bit of time trying to create something that when I take my some vector field, right? So this is going to be equal to question mark, and some normal vector, also equal to question mark. And when I take the dot product of these things, I get out this x plus y squared plus 2z. Oops, I forgot the 2 up here. If I can figure that out, right, what should my f and what should my n be? So that way, when I take this dot product, I get this function that I'm interested in. Well, then I will know what to take the div of, right? Because once I have it set up like this, then I'll have my f, and I can evaluate out the divergence of that, and that's where I will be using divergence theorem. That's why I think that this one's a tricky one. All right, so the first step here is actually that we know something about the normal vector. The normal vector is not as nebulous as the vector field. And so let's think a little bit about the normal vector. Well, it's supposed to be the normal vector, and not just of any old surface, right? It's supposed to be the normal vector of the sphere. Remember, n's really supposed to be a unit normal vector. So I've been saying normal vector a lot, but really I should have said unit normal vector. So let's spend a little bit of time thinking about our normal vector of the sphere. And our boundary surface is going to be x squared plus y squared plus z squared equals 4. In fact, I want to change colors here just to kind of going into a different idea. There's 2 reasonable ways. One's going to take a while longer, but there's 2 reasonable ways to find a normal vector for the sphere. Can anyone tell me what's a way that I could find a normal vector for the sphere? 2 reasonably good answers. So yeah, one option here I see in chat is to parameterize the sphere. Once you have it parameterized, we know the normal vector is given by the cross product of tangent vectors, r sub s cross r sub t. And this would take a while, and we wouldn't then have x's, y's, and z's to stare at the end of it. So yes, this is a very reasonable answer, but it's actually the way that we're not going to head, just because, first of all, it takes longer, and then it'll be hard to translate our x's, y's, and z's. So there's a second way to get a normal vector. That's the way that we are going to go for this one. Anyone remember what that is? I'll tell you, the gradient. So we can use the gradient here. So remember this, like we did back in, this came up in 14.6 when we first were doing this. If we had all of our variables on one side equal to a constant on the other side, then a normal vector is given by the gradient. So the gradient, take a partial derivative with respect to x of our first, partial derivative with respect to x of our function, partial derivative with respect to y of our function, partial derivative with respect to z of our function. So this will be a normal vector. The only problem is I don't know if this is a unit normal vector. So in order to make sure that this is a unit normal vector, I'm going to go ahead and take this, and I'm going to divide it by the magnitude. So that's going to be 4x squared, 4y squared, 4z squared, right? Square each one of my components in my vector, add them together, throw them into a square root, right? That's the magnitude. So I'm going to divide by that magnitude here. So the square root of 4 is just 2. x squared plus y squared plus z squared, the important thing is that we're not just anywhere in space here. We are on the surface. And on the surface of the sphere, we know that x squared plus y squared plus z squared is actually equal to 4. So x squared plus y squared plus z squared here is actually the same thing as 4. And so this is going to be, well, the square root of 4 is just 2. So we're going to have 2 times 2, which is equal to 4. So my unit normal vector then, let's go ahead and just write this, is going to be x divided by 2, y divided by 2, z divided by 2. Again, we needed to take each component and divide it by 4. The denominator, that magnitude there, was 4. All right, in my last statement for this class here, so we want something that when I dot product it with my normal vector, I get out the function x plus y squared plus 2z. In fact, instead of f here, let me go ahead and write a few blanks. Can anyone tell me a vector field that when I dot product it with my normal vector, right? Again, this is supposed to be f dot n here, is equal to my function I'm interested in. What do you like for the first component? 2. Why do you like 2? Well, it's because 2 times x divided by 2 is equal to x. And so that's quite convenient. What do you like for your second component? 2y, yeah. 2y, and that's because when you take that and you multiply it by y over 2, you get y squared. And then finally, I hope everyone likes 4 for the third component. Now that you know what your vector field is, the divergence of it is quite nice, right? The divergence of it is just going to be 0 plus 2 plus 0. Since we're on a sphere, we know the volume equation. 4/3 pi r cubed. Done. So again, challenging problem, especially the first time that you see it, to apply divergence theorem to something that doesn't have a vector field, right? We had to go out and figure out what should the vector field be, to apply the divergence theorem to. So, all right. Anyway, that's enough for today. We have a second day regarding the divergence theorem, so we'll get more practice with this sort of stuff on Wednesday's class. Thanks for sticking around. I'll see you guys on Wednesday.